All right, so get this. Scientists, right? They smashed atoms together at nearly the speed of light.
Oh.
And they found that something as seemingly insignificant as the shape of their nuclei actually mattered.
Interesting.
We're talking about recreating conditions just a millionth of a second after the Big Bang.
Wow.
And discovering that the shape of these tiny nuclei, xenon to be exact, played a key role in the outcome. It's mind-blowing stuff.
Yeah.
We're diving deep into a recent article from the University of Copenhagen's Faculty of Science that details this groundbreaking experiment at CERN.
Oh, cool.
You ready to unpack this?
I am definitely ready.
Yeah. So they're using the LHC to smash these xenon nuclei together.
Okay.
We all know what the LHC is capable of.
Yes.
So what makes xenon so special for this experiment?
So xenon nuclei, they can actually change shape.
Okay.
They can be spherical or stretched out like a rugby ball.
Wow.
Or even squashed.
Interesting.
These shape-shifting abilities, called shape transitions, they're crucial for understanding how nuclei behave.
Right.
And, as it turns out, for understanding what happened in the very first moments of the universe.
Hold on.
Yeah.
They're telling us that the shape of something as tiny as a nucleus matters when you're recreating the Big Bang.
It is a surprising discovery, isn't it?
Yeah.
They expected the extreme energy of the collisions to completely obliterate any trace of the original nuclei's shape.
Right.
But their data only made sense if the xenon nuclei retained their unique structure even at those insane temperatures.
Okay, I'm hooked.
Yeah.
What exactly did they find? Tell me more about this unexpected result.
So they discovered that the xenon nuclei actually held on to their football shape during the collisions.
Okay.
Now, this might sound like a minor detail, but it has profound implications. It challenges some basic assumptions about how much the initial state of matter influences these high-energy collisions, suggesting that even the tiniest details can have a massive impact.
So, if I'm understanding this correctly, the shape of the nuclei acted like a mold for the quark-gluon plasma that formed in the collisions.
Yeah.
Kind of like how using a different-shaped baking pan will result in a different-shaped cake, even with the same ingredients.
That's a great analogy.
Really?
The shape of the nucleus, which is dictated by the interactions between the protons and neutrons within it, directly impacts how the quarks and gluons are distributed during the collision.
Okay.
And that, in turn, influences the properties of the resulting quark-gluon plasma, that primordial soup thought to have filled the early universe.
This is where I always get tripped up.
Oh, yeah.
The quark-gluon plasma.
Yeah.
It's such a bizarre concept. Can you remind me why this soup is so important for understanding the universe's origins?
So think back to the very beginning.
Okay.
A millionth of a second after the Big Bang.
Wow.
The universe was incredibly hot and dense. And matter existed in this exotic state we call quark-gluon plasma. As the universe expanded and cooled.
Okay.
The quarks and gluons in the QGP combined to form the protons and neutrons that make up atoms today.
Right.
So studying QGP is like looking back in time,
Interesting.
trying to understand how the building blocks of matter first came together.
Okay, that makes sense.
Yeah.
So by studying how these xenon nuclei with their unique shapes interact at these extreme energies, we're essentially gaining a glimpse into the processes that govern the formation of the very first atoms.
Exactly.
Wow.
And what's even more fascinating is that this particular experiment focused on a specific characteristic of QGP.
Okay.
Its viscosity.
Okay.
Earlier experiments at the LHC showed that QGP behaves like a perfect liquid with almost zero viscosity, meaning it flows with practically no resistance.
A perfect liquid. That's pretty mind-blowing.
Right.
So if you could somehow stir it, it would just keep swirling forever.
You got it. It's unlike any liquid we encounter in our everyday lives.
Right.
And that's precisely why understanding its properties is so crucial. It helps us paint a picture of how the universe evolved from a uniform soup into the stars and galaxies we see today.
Okay, so we've got this incredibly hot,
Yeah.
dense soup of quarks and gluons behaving like a perfect liquid.
Right.
And the shape of the xenon nuclei used in the experiment is giving us insights into the properties of this soup. But how does that connect to the bigger picture of the universe's evolution?
Okay.
How do we go from a perfectly smooth soup to a universe with planets, stars, and galaxies?
Yeah. That's the million-dollar question.
Right.
And it's what makes this research so compelling.
Right.
See,
Yeah.
if the early universe was filled with this perfectly smooth, free-flowing QGP, It should have resulted in a uniform distribution of matter.
Okay.
Everything would be spread out evenly.
But we know that's not the case.
Exactly.
Our universe is full of clusters and clumps,
Right.
Galaxies and stars.
Yeah.
So how do we reconcile this perfect liquid with the reality of a universe that's anything but uniform?
That's where things get really interesting.
Okay.
There must have been some tiny imperfections, some fluctuations in that early universe that acted as seeds for the formation of larger structures. Think of it like those little imperfections on a snowflake that guide its intricate, unique pattern.
So even though the QGP was flowing smoothly, these tiny imperfections acted as gathering points for matter?
Right.
Allowing it to clump together and eventually form stars and galaxies.
Precisely.
Wow.
And by studying the properties of the QGP, particularly how it responds to these tiny imperfections, we can gain insights into the mechanisms that drove the formation of the structures we see in the universe today.
This is where I have to ask. How does smashing xenon nuclei together, even at these insane energies, actually tell us about these tiny imperfections in the early universe? Seems like a huge leap.
It might seem that way, but remember, the shape of those xenon nuclei affects the properties of the QGP created in the collisions by carefully studying those properties. Researchers can extract information about how the QGP would have behaved in the early universe, including how it would have responded to those tiny fluctuations.
Okay, so we're learning about the universe's first moments by studying the behavior of these tiny nuclei and the QGP they create. But there's another layer to this research that I find fascinating. The computational challenge. You mentioned that these collisions produce a massive amount of data. Tens of thousands of particles.
That's a lot of data.
How do scientists even begin to analyze that much information?
It's a truly remarkable feat of data analysis. Imagine trying to track the movements and interactions of tens of thousands of particles. All moving at nearly the speed of light. It's a computational nightmare.
Oh, I bet.
Even with supercomputers.
So how did they manage to make sense of this deluge of data? Did they need to build a supercomputer the size of a planet?
Actually, they took a different approach. And that's what makes their achievement so impressive. Instead of relying solely on brute force computing power, they developed a new algorithm that allowed them to analyze the data more efficiently by focusing on the correlations between 6 particles rather than just 3, as in previous attempts.
So it's not just about bigger computers. It's about smarter algorithms.
Absolutely.
That's a really important distinction.
It highlights the ingenuity and problem-solving skills of these researchers. They found a creative solution that allowed them to overcome a seemingly insurmountable computational obstacle.
This new algorithm, is it specific to this experiment, or could it have broader applications in other areas of science?
That's the exciting part. This breakthrough has the potential to revolutionize data analysis in a wide range of fields.
Wow.
From astrophysics to climate modeling to genetics.
Really?
Anytime you're dealing with complex systems and massive data sets, this algorithm could be a game changer.
It sounds like this research is pushing the boundaries, not just of our understanding of the early universe, but also of what's possible in terms of data analysis. That's quite a legacy.
Indeed.
Wow.
And what's particularly fascinating is how this seemingly esoteric study of nuclear structure has far-reaching implications. It's a testament to the interconnectedness of different scales in physics. We're learning about the universe's grand beginnings by studying the behavior of these tiny nuclei. And the insights we gain from this research can inform our understanding of everything from the formation of stars to the fundamental forces that govern the universe.
Wow.
But there's one more aspect of this research that I think you'll find particularly intriguing.
Oh, there's more. You definitely got my attention. What else can we learn from these shape-shifting xenon nuclei and their wild dance at the edge of reality? All right, so lay it on me. What's so intriguing about these shape-shifting xenon nuclei?
Remember how we talked about xenon's ability to transition between different shapes? Well, it's not just a quirky feature. Those shape transitions are actually a window into one of the most fundamental forces in the universe, the strong nuclear force.
Okay, you've lost me a little. We're talking about the force that binds protons and neutrons together in the nucleus, right? How does the shape of a nucleus tell us anything about that?
So think of it like this.
Okay.
The shape of a nucleus.
Yeah.
It's a direct result of the interplay between the strong force and the other forces acting within the atom.
Okay.
It's a delicate balance, a bit like a tug-of-war when that balance shifts.
Yeah.
The nucleus can change shape.
So by studying how the shape of the nucleus changes, we can learn something about the forces that are causing those changes.
Exactly.
Including the strong force.
It's like having a tiny, ultra-sensitive force gauge built right into the nucleus. And the fact that these xenon nuclei maintained their football shape even during those high-energy collisions at the LHC.
Yeah.
That gives us incredibly valuable data for understanding these shape transitions.
Okay.
And by extension, the strong force itself.
It's amazing to think that something as seemingly simple as the shape of a nucleus can tell us so much about the fundamental forces that govern the universe.
It is, isn't it?
Yeah.
It's a perfect example of how seemingly insignificant details can hold profound insights.
Right?
And what's particularly exciting is that this research has opened up new avenues for studying the strong force. We're not just limited to theoretical models anymore.
Okay.
We can actually observe its effects on the shape of nuclei under extreme conditions.
It sounds like we're on the verge of a whole new era of nuclear physics.
Yeah.
All thanks to these shape-shifting xenon nuclei. What are some of the potential implications of this research going forward?
Well, the possibilities are truly vast, for one.
Yeah.
This research could lead to a more complete understanding of the nuclear processes that power stars.
Interesting.
Imagine being able to unlock the secrets of stellar evolution by studying the shape of tiny nuclei.
That's mind-blowing.
It really is.
From the smallest scales to the largest, it's all interconnected.
Precisely.
Wow.
And on a more fundamental level, a deeper understanding of the strong force could shed light on some of the biggest mysteries in physics, like the nature of dark matter and the origin of the universe itself.
This deep dive has been an incredible journey.
It has.
We've gone from football-shaped nuclei to the heart of the Big Bang.
Wow.
Explored the mysteries of the strong force, and even glimpsed the future of data analysis. What a wild ride.
It's been a pleasure sharing these insights with you and our listener.
Absolutely.
It's a testament to the power of scientific curiosity and the ingenuity of researchers who are constantly pushing the boundaries of what we know.
If there's one thing I've learned from this deep dive, it's that we should never underestimate the power of a seemingly small detail.
Absolutely.
Who would have thought that the shape of a nucleus could hold such profound secrets about the universe?
It's a reminder to all the learners out there to stay curious, keep exploring, and never stop asking questions.
Right.
The universe is full of wonders waiting to be discovered.
And if you're eager to delve deeper into this fascinating research, be sure to check out the full article from the University of Copenhagen's Faculty of Science.
Definitely.
It's a truly mind-expanding read.
It is.
Thanks for joining us on this deep dive into the world of nuclear physics and the early universe.
Yeah, thanks for listening, everybody.
Until next time, keep exploring